Welcome back to AI.Code.Cast, where we break down those daily coding challenges.
Yeah.
And today, we've got a real brain tickler.
We do.
Figuring out the shortest subarray within a given array whose sum is at least some specific value, k.
Yeah, this isn't just some theoretical, puzzle you'd find in a textbook or something.
Right.
This type of problem actually pops up in real-world scenarios.
Interesting.
Like data analysis and signal processing.
Ah.
So think about it like you're analyzing a stream of stock prices, right?
Okay.
And you're trying to find the shortest period where that price increased by at least K%?
Okay, that's a great example.
Yeah.
So just to clarify, we're given this array of numbers, could be positive or negative.
Right.
And then a target sum k.
Yep.
And we need to find the shortest possible contiguous
chunk,
the subarray.
Array.
That adds up to at least k.
Exactly, and the fact that we can have negative numbers in there, that's what makes it tricky.
Right.
If we only had positive numbers, a simple sliding window would be fine.
Right.
But those negative numbers, those throw a wrench in things.
Yeah, you really do.
They do.
So where do we even begin with this problem?
Well, I mean, we could always start with the brute force approach, which is kind of like trying every key on a giant keychain until you find the one that unlocks the door.
Gotcha. So we would just systematically go through every single possible subarray, calculate its sum, see if it meets our criteria.
Precisely.
Okay.
We'd start at, the first element, then the first two elements, first three, and so on and so on.
Straightforward, but I have a feeling it's not the most efficient.
You are absolutely right about that.
Okay.
The time complexity of this approach is O of n squared, where n is the length of the array. So as that array gets larger and larger, the number of calculations just skyrockets.
Right.
It makes it really slow.
So brute force kind of sets the baseline.
It does.
But we need something smarter.
We do.
More efficient.
Yes.
So what's the next step up from there? Any hints?
Any hints?
To kind of nudge us in the right direction.
Well, here's a thought.
Yeah.
What if we had a way to quickly calculate the sum of any subarray without having to add up all the elements each time?
That would certainly speed things up.
Yeah.
It's like having a running total on your shopping receipt.
Oh, yeah.
You instantly know how much you've spent.
Exactly.
At any point.
That's a good way to put it.
So are we thinking some kind of data structure?
Which
gives us that running total.
I think you're on the right track.
Prefix sums.
There you go.
So we're calculating the cumulative sum of the array elements
that's right.
up to each index.
It gives us that quick way to get the sum of any subarray.
So prefix sums are like our cheat code.
They are?
For calculating subarray sums.
Exactly.
But how would we use those?
Yeah, that's the question.
To find the shortest subarray.
That is the question.
Because we can quickly determine the sum of any subarray, but we still need to
search for the shortest one.
Yeah, efficiently.
Efficiently.
Any thoughts on how to approach that?
Imagine you're trying to find the shortest route to the top of a hill. You wouldn't want to start
from the highest point you've already reached.
Right.
No, it makes more sense to start lower.
Yeah.
Minimize the distance.
You're getting it.
Okay.
So we need a way to kind of keep track of those potential starting points for our subarrays.
Right.
And efficiently discard the ones that are less optimal.
So some system that helps us maintain order and eliminate less promising starting points as we go.
Exactly.
This is starting to sound familiar.
Oh, is it?
Is it time to bring in the monotonic queue?
You got it. Okay, so
a monotonic queue could be our key to efficiently tracking and managing those starting points.
Okay.
But let's save those details of how that works for part 2 of our deep dive.
All right. I'm already intrigued to see how a monotonic queue fits into all of this.
Yeah.
So we've laid the groundwork.
We have.
Brute force, prefix sums.
Yep.
Now we're ready to move on to this more sophisticated solution.
Absolutely.
All right. Sounds good.
Looking forward to it.
Me too.
Welcome back to AI.Code.Cast.
Back again.
Last time, we left off talking about this idea of using a monotonic queue to solve our shortest subarray problem.
Right.
We figured out brute force is way too slow. And that prefix sums give us that speed boost, but we still need to figure out a way to manage those potential starting points.
Yeah, efficiently.
For the subarrays.
So that's where the monotonic queue really shines.
Okay.
Imagine you're in a line
Okay.
And anyone shorter than the person behind them politely steps aside.
Okay.
That's kind of how a monotonic queue works.
Gotcha.
It keeps things in order.
Okay.
In our case, increasing order of prefix sums.
So we're not just throwing prefix sums into the queue randomly.
No.
There's a specific order.
Absolutely.
Okay.
We'll use a Deque to implement our monotonic queue.
Okay.
Which allows us to add and remove elements from both ends.
Right.
That flexibility is key for maintaining the order.
Gotcha.
Okay, so how does this ordered queue actually help us?
Yeah, how does it help us find the shortest subarray?
Well, think of it like this.
Okay.
The monotonic queue is like a filter.
Okay.
It's constantly discarding those starting points that are less likely to lead to the shortest subarray.
So if we have two potential starting points, and the one with the smaller prefix sum comes later.
It's always a better choice.
Precisely.
Okay.
Because for any future endpoint, we might consider the subarray starting at that later index.
Right.
With the smaller prefix sum.
Yeah.
It's going to be shorter.
Right.
And have an equal or greater sum.
Okay. It's like choosing that lower starting point.
Exactly.
On that hill climb.
You got it.
Makes sense.
So how do we actually use the monotonic queue as we process the prefix sums?
Yeah.
Well, we'll iterate through our array of prefix sums.
Okay.
And for each one, we'll do a few things.
Okay.
First, we'll check if we can form a valid subarray using the elements already in the queue.
Okay, so we're looking at the difference between the current prefix sum and the smallest one in the queue.
Which is at the front, yep.
If that difference is at least k,
yes,
then we found a subarray that meets our criteria.
Exactly. Yeah. And then if we find a valid subarray, we got to check its length against the shortest length we've seen so far.
Right.
If it's shorter, we update our minimum length.
So we're constantly refining our search.
Exactly.
Zeroing in on the shortest possible subarray.
You got it.
Okay.
Then comes the crucial part, maintaining that monotonic order of the queue.
Right.
We compare the current prefix sum to the one at the back of the queue.
And if the current one's smaller, we kick the one at the back out.
You got it.
Okay.
Because remember, a later starting point with a smaller prefix sum.
Right. Always more promising.
Always more promising. Exactly.
Okay.
And finally, we add the index of the current prefix sum to the back of the queue.
Gotcha.
So we're sliding that window through our prefix sums, using the queue to keep track of those most promising starting points.
Okay.
Constantly updating that minimum length as we find better subarrays.
This is a really clever approach.
It is.
But can we walk through a concrete example?
Of course, yeah.
To really solidify our understanding. Absolutely. Let's say our array is 2 minus 1, 2. And our target sum k is 3.
Okay.
First, we'll calculate the prefix sums, which would be 0, 2, 1, 3.
Got it.
Okay.
So we got our prefix sums.
Yep.
We're ready for the monotonic queue.
Bring in the queue.
Right.
Initially, our queue is empty.
Okay.
Our minimum length is set to infinity.
Okay.
We start with the first prefix sum, which is 0.
Right.
Since the queue's empty, we just add its index to the back of the queue.
So our queue now has 0.
It does.
Okay, let's move on to the next prefix sum, which is 2.
Okay.
Can we form a valid subarray using this and what's already in the queue?
Well, the difference between the current prefix sum, 2, and the prefix sum at the front of the queue, also 2, is 0.
Yeah.
Which is less than our target sum of 3.
So not yet.
Not yet.
Okay.
So we move on to maintaining that monotonic order.
Okay.
We compare 2 to the prefix sum at the back of the queue, which is also 2, 3. They're equal.
Yeah.
So we don't remove anything.
Okay.
And we add the index of the current prefix sum to the back of the queue.
So our queue now contains 0, 1.
0, 1, that's right.
Okay.
Now let's consider the third prefix sum, which is 1.
Oh, right.
Again, we can't form a valid subarray yet.
Right.
But when we check for monotonicity, we see that 1 is less than 2, which is at the back of the queue.
Right.
So we got to remove 1 from the queue to maintain that increasing order.
Got it.
So our queue is back to 0.
Back to 0.
And finally, we arrive at our last prefix sum. 3. 3, okay. The difference between 3 and the prefix sum at the front of the queue, 2, is 1. Which is still less than our target sum of 3.
Right.
But remember, the last prefix sum represents the sum of the entire array.
Oh, that's right.
Right.
Okay, yeah.
So we consider the entire array as a potential subarray. Its length is 3.
Yeah.
Which is less than our current minimum length of infinity.
Right.
So we update our minimum length to 3.
Fantastic.
We've reached the end of our prefix sums, and we can confidently say that the shortest subarray, with the sum of at least 3, has a length of 3.
Awesome.
It's remarkable how this algorithm just gracefully handles situations where the shortest subarray is the entire array itself. And it does it all in a single pass through the array.
I'm really impressed by the elegance and efficiency of this.
It's pretty neat, monotonic queue approach.
But are there any other data structures we could use to solve this?
That's a great question, and it leads us perfectly into the final part of our deep dive. While the monotonic queue is incredibly efficient, there are alternative approaches that use different data structures, each with their own set of trade-offs.
We'll explore those in part 3.
All right. I'm excited to see what other tools we can use and how they compare to our monotonic queue champion.
It'll be fun.
All right, sounds good. Welcome back to AI.Code.Cast.
We're back.
We've been really breaking down this shortest subarray problem.
We have.
And
we've seen the brute force approach. We've seen that elegant monotonic queue solution.
The monotonic queue really efficiently manages those potential starting points. Helps us find that shortest subarray in linear time.
It does.
But you mentioned there are other approaches. Using different data structures. So I'm curious how those compare.
All right, so one alternative approach involves using a min heap. Or a priority queue.
A min heap.
The idea is similar to the monotonic queue approach. But instead of a Deque, we'll use a min heap to keep track of our prefix sums.
A min heap.
So I usually associate min heaps with finding the smallest element in a set. So how does that translate to shortest subarray?
So here's how it works. As we calculate each prefix sum, we insert it into our min heap, along with its index in the original array.
So each element in the heap is like a pair prefix sum and its index.
Yes, and by having those indices, we can easily calculate the length of the subarrays. And the beauty of a min heap is that it always gives us access to the smallest prefix sum at the root. So it's like we have this constantly updated list of the most promising starting points.
Just like with the monotonic queue?
Just like the monotonic queue. So as we iterate through those prefix sums, we'll compare the current prefix sum with the minimum prefix sum at the root of the heap. If that difference is at least k. We found a valid subarray.
That familiar check. There it is.
Let's see if we meet our criteria.
Exactly. Then we calculate the length of that subarray using the indices stored in the heap, and we update our minimum length if necessary.
So the min heap, just like the monotonic queue, it helps us keep track of those potential starting points.
It does.
And discard less optimal ones.
Both approaches actually achieve a time complexity of O(n) log n. Due to the operations on the heap or the Deque. While that's quite efficient, it's not as fast as the O(n) complexity.
The monotonic queue. Still holds that speed crone.
It does.
But the min heap approach might be a little bit more conceptually accessible.
Yeah, it could be. It could be.
To some.
The choice often depends on, personal preference and the specific problem constraints.
I really love how we've explored these different approaches. It's clear that there's not always a single best solution.
So understanding those trade-offs and the nuances of each approach is really key.
It is. The goal is to build up that diverse algorithmic toolbox. So you can choose the right tool for the job.
Well, this deep dive has been a fantastic exploration.
It has.
Of algorithms and data structures.
Absolutely.
We've gone from brute force to the elegance of the monotonic queue, even delved into the world of min heaps.
We did. We hope you enjoyed this journey and learned something new along the way.
Definitely.
And remember, the best way to really solidify your understanding is to implement these algorithms yourself. Experiment with them.
Play around with it.
Exactly.
Well, thanks for joining us on AI.Code.Cast.
Thanks for being here.
We'll be back.
We will.
With another exciting code challenge.
Yes.
Tomorrow.
See you then.
Until then, keep coding and keep learning.
Absolutely.